Welcome to educator.com. This lesson is about slope and direct variation. In this lesson, you will learn the relationship between slope and direct variation. Applications are that you can understand the relationship between two quantities whose ratio is always the same. And this could be a situation such as the price of a product and the total sale price. So as the amount of the product increases that you're buying, so will the amount of the total sale price. Direct variation is a linear function in which the ratio of two quantities is always the same. So there's no exponential growth. It's just a constant variation between the two. Identifying a direct variation. So let's look at what a direct variation would look like in a math problem. The relationship between the number of pounds of grapefruit squeezed, x, and the ounces of grapefruit juice made, y, is a linear function. So the more pounds of grapefruit that you squeeze, the more ounces of juice will be outputted. The table shows some solutions to the function. Is the function a direct variation? So first, let's find the ratio of the two quantities. The first one would be 12 over 2. Remember to put y over x, and that would be 6. 18 over 3 equals 6, and 30 over 5 equals 6. So it seems that the ratio of the two quantities always simplifies to 6. So it would be a 6 to 1, actually, if we were going to keep it in ratio form. Find the slope. Well, remember that in the last unit you could use any two values which represent a coordinate pair, so x, y. So this one would be 2, 12, and this one would be 3, 18. And remember the formula for slope is m equals y2 minus y1 over x2 minus x1. And the y2, this is x1, y1, x2, y2. So y2 here is 18 minus y1 is 12 over x2, 3 minus x1 is 2. 18 minus 2 is 6, and 3 minus 2 is 1. So your slope is also 6 over 1, or 6. So we found the slope, which was 6 over 1, and we found the ratio, which was 6 over 1. And do they equal? Yes. So is this function a direct variation? Yes, it is a direct variation because the change or the relationship between the quantities stays constant. It's always 6 over 1, 6 over 1, 6 over 1. Let's look at some more slope and direct variation. A store sells grapes for $2.50 per pound. Graph the relationship between the amount of grapes purchased, x, and the total cost, y. Find the slope of the line and explain what it represents. Well, first we need to make a table to find solutions. But let's write out our function so we know what equation to use to substitute our input to find our output y. So the total cost is y, and the amount of grapes purchased is x. So that's varying. What doesn't vary is that it always costs $2.50 per pound. And it depends based on, the price will change based on how many pounds, how many x pounds are bought. So now let's make a solution, make a table to find solutions. So x input, y output. Remember that you only need 2 points to make a line. So always, I think it's easy to use x as 0. If you buy 0 pounds of grapes, you get a 0 for a total cost. And then it's easy to use small numbers, 1. And then if you buy 1 pound, it will cost $2.50. I'm going to shorten it to 2.5. So when I graph 0, 0, and 1, 2.5, it'll be easier. Graph the points on a coordinate plane. So we just found one. We've made a table of two solutions. And now I'm going to graph the points on a coordinate plane. So I have my x-axis and my y. And luckily my values are small, so my graph can stay small. It starts out at 0, and then 0, 0, and then the next point is 1 and up 2.5. Okay, I'm going to use the straight edge to connect the two lines. That wasn't too straight, I guess, but you get the idea. So we've graphed the points on a coordinate plane. Now we're going to use the points to find the slope of the line. So I'm going to use m equals y2 minus y1, change in y, over x2 minus x1, change in x. So here's x1, y1, x2, y2. So 2.5 minus 0 over 1 minus 0 equals 2.5 over 1. And that simplifies just to 2.5. So the slope is 2.5. And does the slope of the line represent the unit cost? Does it represent how much it costs for 1? Well, see, the slope is 2.5, and now let's look at the unit cost. Remember, unit means for 1. $2.50 for 1 pound. The slope is 2.5. So does the slope of the line represent the unit cost? Yes, it does. The slope tells you how much each pound costs. So here you can understand the relationship between slope and direct variation more. The slope will tell you how much for 1, for the unit. Is the linear function in this table a direct variation? So to find direct variation, we're going to look at the ratio of y over x. In this case, it would be 0 over 0, which is undefined, so that's not a good one for us to look at. The next one would be 2.5 over 1. The next one would be 5 over 2, which simplifies to 2.5 over 1. And the last one would be 7.5 over 3, which simplifies to 2.5 over 1. So is it a direct variation? Well, when x is not 0, we can see that the ratio is 2.5 to 1, 2.5 to 1, 2.5 to 1. So yes, it is a direct variation because the ratio stays constant. The ratio, the relationship between the two values represented by this ratio never changes. So it is a direct variation. Is the linear function in this table a direct variation? Well, let's look again. Let's make it y over x. Let's look at the ratio. 20 over 2 simplifies to 10 to 1. You don't want to simplify this down to a single number 10 because remember that we're looking at a ratio, and a ratio is a comparison of two quantities. If I were to simplify it to just 10, I would no longer have two quantities. So you want to keep it 10 to 1. 25 over 3 does not simplify to 10 to 1, and neither does 30 over 4. So is this a direct variation? No. So for example, 25, 3 doesn't go in, goes in 8, and I'm left with 1. So it would be 8.33 over 1 here. So once again, that is not going to be the same as 10 to 1. So I can stop there. I already know it's not going to be a direct variation. We're going to graph the direct variation x equals negative 3p and find the slope of the line. Now in this equation we have to be really careful because they didn't give us this typical y output and x input. What they gave us instead here is an x to represent the y output, which is typically represented by y, and a p to represent the x. So later when we graph it, we're going to be using x and p rather than y and x. So we're going to graph the direct variation by creating the input p and output x table. I'm going to choose 0, 1, and 2 because those are easy numbers to work with. Remember that you only actually need 2 points, maybe the 0 and the 1 or the 1 and 2, because just 2 points will create a line for you. So x equals negative 3 times 0, which is 0. And then x equals negative 3 times 1, which is negative 3. And then x equals negative 3 times 2, which is negative 6. So we have 3 coordinates that we can graph now. And remember that the output is represented by x in this case, and the input was represented by p. Be careful with your labeling. I need my x to at least go down to negative 6. So 1, 2, 3, 4, 5, 6, 7. And my p to go over to at least 2. 1, 2, 3. So at 0, 0, there's a point. At 1, negative 3, there's a point. And at 2, negative 6, there's a point. So I have 3 points here to create the graph of my direct variation. And that represents x equals negative 3p. So we've graphed the direct variation. Now let's find the slope of the line. Remember that you can find the slope, m equals y2 minus y1, the change in y, and x2 minus x1. Now in this case, remember that the y2 minus y1 represents the rise. So although it's labeled x, it still is discussing the rise. And x2 minus x1 is the run. So though it's labeled p, it's still representing the left and the right. So I'm going to choose two coordinates. Let's take 1, -3, and 2, -6. And I'm going to label it x1, y1, and x2, y2. Although they are not x and y coordinates here, they're actually p and y coordinates, we can still use that so that we can substitute into this equation. So it's going to be -6 minus a double negative here, -3, because the equation already includes a negative. And then that's going to be over x2, 2 minus 1. So especially with a case with double negatives here, it's very helpful to label x1, y1, x2, y2 so that you can come and just do a very simple substitution here. -6 plus 3 is -3, and 2 minus 1 is 1. So your slope is -3. So we found the direct variation, the graph of it, and then we've gone and also found the slope, which is -3. Suppose you run 5 miles each day. Graph the relationship between the number of days passed, x, and the number of miles you ran, y. Find the slope of the line and explain what it represents. Okay, so here they went back to the traditional x input and y output. So you run 5 miles each day. So it's going to be y, the number of miles, equals 5 times the number of days. Find the slope of the line and explain what it represents. So the slope of the line here is, I'm going to create the graph, 0, 1, 2. So if I ran 0 days, I have 0 miles. If I ran 1 day, I have 5 miles. If I ran 2 days, I've gone up to 10 miles. So let's find the slope. I'm going to use these two as my coordinates, 1, 5 and 2, 5. Ooh, 2, 10. And remember your equation for slope is y equals, or m represents slope, equals change in y, rise over change in x, run. x1, y1, x2, y2. So 10 minus 5 over 2 minus 1. 10 minus 5 is 5, and 2 minus 1 is 1. And that slope simplifies to 5. Notice over here as a reminder, I labeled the coordinates. It's good to do that because one of the most common mistakes that people make is just by inputting the coordinates into the wrong place in the equation. So just in the beginning to make sure that you always label. You can keep track of that. And lastly, they said they wanted us to find the slope, which we did, 5, and explain what it represents. This 5 represents the direct variation between the number of days and the total miles run. Because the slope, 5, represents the unit. So for 1 day, it's 5 miles. And it increases at a constant rate of 5 miles for every additional day. So the slope of the line here represents the direct variation, or also the unit. Thank you for watching educator.com.